14 years ago, the European Southern Observatory announced an exoplanet with remarkable properties. And today we are going to talk about this very specific exoplanet, why it's so remarkable, and what its properties could mean for our home planet if we would live in a similar scenario. So let's hop into science and universe sandbox in today's session. Let's go. Hi everybody, Thomas here, and today I would like to talk about an exoplanet called, I'm not really sure how to pronounce it, but I think it's called the Gliese 667cc. The first C, capital C, the second C, a smaller, lowercase c. And this planet is revolving around the star Gliese 667c. And why the C? Well, the star is a part of a triplet star system, a larger one of the Gliese 667 system, where we have we have 3 stars in some kind of loose bound flying through the Milky Way. The interesting thing is that Gliese 667cc is living in the habitable zone. And today we will take a look at the habitable zone. What is it exactly? And also have a look first at the planet, what the planet is all about and why it is so fascinating, and maybe also not the perfect place to be, although it's in the habitable zone. So I would say we are switching now to some slides and some very short presentation I would like to give you about the Gliese planet and give you an overview what's so strange about it. Well, now, first of all, this is not an actual image of the surface of Gliese 667cc. It's an artistic impression, and this is an artistic impression I obtained from Wikipedia, to be very honest. But I think, this kind of things, they always give you some kind of feeling what or how a world could look like. And well, the planet is around 23 light years away in the constellation of Scorpius. Well, doesn't matter for now because we won't reach it in the far future anyway. But the interesting is that it has a massive mass, let's say. Yeah, it is assumed that it has around 4 times the mass of Earth and also around the 1.5 radii of our home planet. And the thing is, it is in the habitable zone, so in the zone where liquid water is possible. So in this zone, we have radiation from a host star where water can exist between 0 and 100 degrees Celsius. Now we will take a look at Universe Sandbox just in a moment to show you where the Earth is placed in the solar system. But for now, we know that this planet is in the habitable zone of its host star, namely Gliese 667c. The interesting thing about Gliese 667c, though, is that it's a red dwarf star. So it's way, way smaller, way fainter than our own home star. And it revolves around the star not at, let's say, 1 AU, so 150 million kilometers like our home planet around our sun, but only a tenth of it, so around 15 million kilometers. In our solar system, this would be a death sentence, of course, but in this system there, it is, of course, necessary because the host star is not really that strong and not pushing enough energy into the different planets. And to have a look at the star system, well, we will not rebuild it. We will take a look at our home planet Earth because there is one particular case that could make this planet not very habitable. Of course, it could be habitable in a very theoretical sense, but it wouldn't be as pleasant as our home planet. And for this, I would say we go to Universe Sandbox because there I can show you a concept that's very important to know, because this concept or this idea of what's happening astrodynamically is very particular for planets that are revolving around red dwarf stars. Yeah, although they live for 100 billion of years, the planets also can coexist there, but due to some astronomical reasons, due to some so-called tidal effects, we have a particular case that leads to, I would say, almost very destructive world properties. So, without further talking, let's switch to Universe Sandbox so I can show you what I'm talking about. Our solar system, the starting screen view of universe Sandbox. And here we have our home planet Earth. And to take a look at the habitable zone, let's go to a top view. We can simply go here to view. And then we go here to the habitable zone, where we see the different areas where things are very pleasant in our solar system. And as you can see, even our Earth is not really in the center of the habitable zone. It's a little bit closer than, let's see, normally. But anyway, a planet that is way closer is, of course, Venus, which is very heated up. But the reason here is not only that it's closer to the sun, it's also due to its atmospheric properties, like it has a lot of CO2 and other gases that trap the radiation quite well. And then, of course, we have other planets like Mars that are in the habitable zone, but are kind of cold because, well, there's no magnetic field protecting the atmosphere, and the atmosphere is super thin, ultra thin, basically not existing. So the temperature is varying a lot during the day, Mars Day. And of course we have Mercury, but Mercury is basically a big rock very close to the sun. Now the thing is, if we click here on the home planet Earth, we can also click to the surface where we see the temperature. We can, for example, click here and then also to show object data view. So we have the surface temperature here on the left-hand side. It's not 100% correct, maybe a little bit exaggerating the negative temperatures with minus 80 degrees, especially here in the mountain ranges and so on. But let's say it's okay for the purpose, for the thing I would like to show you. Because one thing that happens around dwarf stars is that the planets go into something called the tidal lock. So our home planet Earth, as you can see here, is revolving around the sun at around 365 days plus minus a few hours, right? But a day on our home planet is around 24 hours. So during 1 year, we have 365 revolutions around ourselves. Yeah, so it's kind of nice to have not only, let's say, 2 working days a year or so, but yeah, it's 24 hours basically. And the thing with the tidal lock is that the tidal lock leads, based on some tidal effects, leads to the result that 1 year around a star corresponds to 1 day on the planet as well, which means that the planet is facing one side always to the sun and the other side is always facing to the dark cosmos. We have something that is really present in the vicinity of our home planet. It's basically the moon itself, because the moon always shows the same side. Of course, there's some variations, some wobbling and stuff like that if you simulate it for a longer period of time. But the thing is that also the moon is tidally locked to our home planet. And this constellation is something we have around red dwarf stars. Now, what happens with Earth? What happens with the temperature if we are tidally locking this situation? Now, in Universe Sandbox, we cannot really simulate this part in the long run, but what we can do, we can simply go to motion, and then we can simply click here on tidally lock. Yeah, so it means that the rotation period is equal to the orbital period. And when we do this, we will see on the left-hand side how the surface temperature of our home planet changes drastically. We can maybe increase a little bit the view. Maybe it's not working well with the... okay, it's auto-expanding. Nice. So I would say we can leave it with 16 days per second, maybe reducing it maybe to around 10. And then we click on tidally locking and we see what will happen. We see that, first of all, nothing, because I didn't click. Wait, did I click on it? Yeah, I think so. Yeah, I click on it because you can already see how the temperature changed. We have one spot. Now here in this case, it's the Pacific Ocean, where this is the part that's facing towards the sun. And the other part, Africa and also Europe and Asia, they are facing towards the cosmos. You can see also here on the Earth that one side is really covered in ice, while the other side is, well, we don't see really how everything is evaporating, but believe me, it is evaporating. And over the time, we see, of course, that the temperature is increasing and increasing. And if we leave this for a few years or even a few months, then this temperature will increase higher and higher, while the colder area is basically not habitable anymore for any life. It's way too cold. Now, around dwarf stars, we have a similar situation where we have, of course, this high temperature spot on the one side and the cold spot on the other side. And the thing is that life could emerge on these planets, but the hot spot, let's say, has to have a temperature that is less boiling, yeah, so it should be less than 100 degrees, of course. But on the other side, this doesn't mean necessarily that nothing can evolve at all, because we have some areas that are habitable, like the so-called termination zone. Yeah, so basically the dusk dawn area where the sun is, let's say, very, very low, and we have temperatures, surface temperatures that go maybe around 18 degrees, 20, 30 degrees or something like that. Here we have a ring, let's say, where on the map, a ring where life could exist. On the other hand, though, due to the high differences of the temperature on the night side and the day side, there are probably, if we have an atmosphere, extremely strong winds, like nothing comparable to what we have here on Earth, most likely comparable to what we have on Jupiter or Saturn with hundreds of kilometers per hour. So this would be a very harsh environment. But there's also the theory that life could also emerge in some kind of bacteria or fungi form, also in the atmosphere itself, living and existing based on chemical components and also the light that is in the upper part of the atmosphere. So these things could theoretically work. Intelligent life, or life like we have it here on Earth, complex life, is very unlikely to exist there. As I said, the termination zone is an area, but it's only a fraction of the entire planet. The question is also whether there's liquid water or other components that are necessary for life. But at least you get an idea what it means when we have a tidally locked planet. The point is, here you can really see the termination zone, pretty interesting. The thing is, though, that when you hear some news about other new exoplanets and they are habitable and they are very close and habitable zone, you always have to consider the host star. If it's an M star like our sun, it's a good situation. If we have a red dwarf star, well, the habitable zone doesn't necessarily mean that we have also there's a potential for life at all because of this tidally locked situation. Thanks a lot for listening, and thanks a lot for watching my short science video. There are more videos coming soon, while I'm also preparing some lectures in the university for the NASA Spice Toolkit. So I will provide 2 times 90 minutes of lecture soon. One will be more theoretical part with some slides and a presentation, and the other one will be with some programming in Python. So if you're interested in coding or so, you can also come back here to this channel, because I try to create this mixture of high-level education, high-level space scientific insights, and also some deeper level using also Python. Now, if you like the mixture, please leave a comment. Please also subscribe to the channel. It helps me a lot. And if you have other ideas what you would like to have to see, then of course write it in the comments. More tools, more ideas, more science topics are being covered soon. I'm not sure yet if this very, very high level on the one side and this very deep level with Python on the other side is a good mixture. Maybe something in between is missing, for example, with some showing some equations or mathematical formula. Maybe this is something for you to comment and help me to refine my YouTube channel in the long run. Until then, I wish you nice exploring with Universe Sandbox. If the days are good and clear, go outside, because a meteor shower is coming soon. I would say in 2-3 weeks. I'll make a video about this also soon, so that you won't miss it. And until then, have a nice day. Thanks for watching, and see you next time.